So from our previous video, we highlighted some of the inefficiencies of linear constraint optimization. And I mentioned to you that the simplex method is quite a good way to resolve these inefficiencies. And I'm going to show you now with the use of Excel how to implement the simplex method. And the basic idea is that the simplex method starts with the basic feasible solution and then moves through a sequence of other basic feasible solutions that improve upon each other. Now that's an important point, that each solution improves upon the last. So let's illustrate this. Okay, so what I've done is I've plotted the feasible region for you. So you can see in the shaded blue area where the feasible solution is. Now, we need a starting point. So remember, the simplex method starts with the basic feasible solution. And we can start at this point A, and that is the point that x1 and x2 is equal to 0. Okay, so if we start at that solution, we can solve for each one of our variables. S1, let's use capitals, so S1 will equal to 77, S2 will equal to 80, S3, remember these are slack variables, equals 9, and S4 equals 6. Okay, so we have our slack variables, and we can now begin to move through our solution using a tabular format. Okay, so I'm going to write this in my table here. So you'll notice on the left column we have a basic feasible solution, and you can see we've got Z, which is our profit, S1, S2, S3, and S4, and that's because we started at the initial point A, where x1 and x2 are equal to 0, and here we have all of our variables from x1 to S4. Okay, so I'm going to initially start out with the objective function, which is expressed as Z minus 150 minus 175, 0, 0, 0, 0, with the solution of 0. Okay, so what I've done there is I've taken our objective function Z and I've set it to 0, and I've moved all of my parameters across. So effectively we've got Z minus 150 times x1 minus 175 times x2 minus 0 s1 minus 0 s2 minus 0 s3 minus 0 s4. Okay, so the next step now involves moving to a new basic feasible solution. Now, how we are going to do this is we want to, remember, maximize our objective function, that is, maximize our value Z. Okay, so what would we need to, remember, initially we have x1 and x2 equal to 0. Now, if I want to move to the next solution, I'm going to have to change either x1 or x2 or s1, s2, s3 or s4. Now, I need to think, because this has a negative sign in front of it, so z minus something, if I want to get a bigger value of z, I must subtract more from it. So the next feasible solution for me would be to bring in x2 because it has the largest coefficient in front of it. So if I brought in x2, let's say setting x2 value equal to 1, then I would have to minus 175 from z, which means effectively I'm going to have to increase z to get back to my solution of 0. But I am going to show you this method. From the graphical solution, it is actually quicker to go from left to right and then back to our optimal solution at the extreme point. Okay, so we call the variable that we bring into the solution our entering variable, and the variable leaving the solution as the leaving variable. Okay, so we can develop a mathematical solution to this, or method. Okay, so we can include some important information in our table. So if you recall, we can include a concise summary of our information. So we can include our other inequalities, which by introducing the slack variables, we've made into equalities. So our first one is equal to 7x1 plus 11x2. We introduced our slack variable must equal 77. I'm just going to fill these with zeros. 0, 0, 0. Okay, and it turns out our y-intercept is 11 graphically. Okay, our second inequality, we had 10x1 plus 8x2. We had a introduced slack variable 2, and that was equal to 80. And our y-intercept here is 8, and we do the same for the rest. So here we had x1 needed to be greater than 9, sorry, less than 9. So y-intercept of intercept 9, and sorry, yeah, we had x2 needed to be less than 6. S4 solution 6, okay, and there's effectively there's no x-intercept here. Okay, so now we must choose a leaving variable from our set of equations. And if you recall from our plot, we are moving from left to right. So this is point B from our previous videos. And we know that at point B, the 0 variables are x2 and s2. Okay, so we need to go to s2 in our table and replace it with our entering variable, in this case, x1. Okay, so if I want x1 to be 1 here, I must divide by 10. So this becomes 1. 8 divided by 10 is 0.8. Say 0. This becomes 0.1. And our solution becomes 8. I'm going to leave the intercept for now. Okay, and this changes to, our basic solution changes to x1, because x1 is my entering variable. Okay, so now we can eliminate the other x1 variables above, and you'll notice that this is very similar to the Gauss-Jordan method. So if we do that, we get the following result. Okay, I'll leave that up to you to carry that exercise out. But for time's sake, I've already done this. So x2 is minus 55, x1 is 0, s2 is 15, s3 is 0, s4, our solution is 1200. going to leave the y-intercept, okay, and x2 here is 5.4. S1 stays 1, S2 becomes minus 0.7, that stays 0, oops. Oops, minus 0.7. Excel doesn't like what I'm doing here. There, I should put an apostrophe. Okay, that's something new to me. S3 is 0, okay, and our solution becomes 21. Okay, and then I need to remove this x variable. So this becomes 0, minus 0.8. Oh, did the same thing. 0, minus 0.1. It stays 1, 0. Solution becomes 1. And our intercept becomes minus 1.25. I should include the intercept for the others. So this is 10, and this is 3.89. And this can stay the same. Okay, I'm just going to leave the intercept here as 6. Okay, so now we have our new basic feasible solution, and we can you can see that we've increased our objective function to 1,200. Okay, so we can now use this method again to move to our next, and in this case our final step, and that is only one more variable, x2, that has a negative value next to it. That is this minus 55, and therefore I use this as my entering value and change S1. So S1 becomes my leaving value. Okay, so this becomes x2. Now remember, because effectively, let me just write this row 2 out, is going to be 0x1 and minus 55. I should keep this in here. So this is 0x1 minus 55 x2 plus 0 plus 15 s2. Okay, these are all 0, and I've changed my solution here to 1,200. So now the only negative value is this x2 here, so I should use this as my entering value, because that would also increase this z value here in order to optimize my solution. Okay, so if we do that and carry out Gauss-Jordan on our table, we end up with the following. So and S2, this is S1, (0.1852). Okay, this becomes minus 0.1481. this row becomes positive 1481. This becomes minus 0.1852, and eventually you should end up with a solution. So I'm not going to carry this out, but you'll end up with a solution here with the z value equal to 1413.889, x2 value of 3.889, and a y value of x1 value of 4.889. This becomes 4.11. This becomes 2.11. So you can see that I've located my extreme point here using the simplex method. Okay, I suggest you practice this and make sure you can get similar answers, and you can see that I've maximized my solution, and the reason why I've maximized it is there is no negative values left in my profit term.